Many associate smart buildings with consumer convenience, app-controlled lights, or residential thermostats. At the scale of a massive commercial tower, technical requirements are far more rigorous. Transforming a conventional shell of concrete and steel into an intelligent building requires specific technological shifts. Professionals in the AEC industry define a building's intelligence through the performance and reach of its underlying systems. Identifying these structures begins with a system-based framework that serves as a foundational baseline. These frameworks focus on the networks of automated infrastructure running behind the walls rather than visible user-facing gadgets. Understanding commercial intelligence requires an analysis of how digital subsystems are routed and integrated through the physical structure. To categorize these technologies, the industry relies on two distinct but related methods. One is a practical shorthand used by real estate developers and on-site engineers to manage hardware deployment in the field. The other consists of formal engineering design standards that provide a rigorous technical vocabulary. The Chinese Intelligent Building Design Standard, GBT 50314-2000, serves as the primary text for this categorization. This standard offers a comprehensive benchmark for evaluating system-based definitions on a global scale. We can visualize this by mentally constructing a building from the ground up, moving from simple shorthand to formal standards. True structural intelligence exists at the intersection of practical developer terminology and formal regulatory guidelines. The foundation of the developer shorthand is the 3A framework. In this model, each A represents a specific pillar of automation, often installed as an independent silo. The first pillar is building automation, or BA. As the blue pathways show, this system traces the physical mechanical rooms, HVAC ducts, and security nodes of the structure. BA provides localized control over the building's physical infrastructure. It governs physical systems such as HVAC units, lighting zones, and access-controlled doors. These systems function autonomously to maintain a stable environment without constant human intervention. The second pillar is communication automation, or CA, represented here by the server rooms, vertical fiberizers, and Wi-Fi topologies. CA serves as the high-speed data routing infrastructure for the entire building. While BA manages physical energy and matter, CA manages the flow of information. It handles telecommunications, external internet pipelines, and internal data routing between floors. The third pillar is office automation, or OA. OA refers to the technology layer that supports the day-to-day workflows of the building's occupants. This layer is primarily software-driven and user-facing. Examples include automated workspace scheduling, digital display management, and localized internet portals. Together, the 3A framework establishes the building's autonomous reflexes through BA, its nervous system through CA, and its cognitive overlay through OA. In many projects, these blue, yellow, and green pathways run parallel to each other, remaining completely isolated. Simply installing these three pillars side by side does not create an intelligent building. Without communication between systems, efficiency is lost and data streams can conflict. The GBT 50314-2000 standard provides a regulatory solution to this problem of isolation. The standard addresses system isolation through the requirement of optimal composition. This requires intentional integration of automation systems, fusing them with the building's structural wireframe. In an integrated building, an OA scheduling system can send a data packet over the CA network, telling the BA HVAC system to cool a room before a meeting begins. This technological mesh must also connect to overarching building service and management protocols. The formal standard treats intelligence as the emergent result of total systemic integration. We can now evaluate the external outputs required by the standard, indicated by these 4 data tags on our unified structural mesh. An optimal composition must produce 4 specific outcomes for the end user. The first is high efficiency. Integrated systems must optimize energy use and lower operational costs over the building's lifecycle. The second is comfort. Systems must adapt dynamically to maintain thermal and lighting baselines for occupants. The third is convenience, defined as frictionless interaction between the occupant and the building's networks. The fourth is safety. The building must mount integrated, automated responses to both physical and digital threats. These 4 outcomes are the empirical proof of intelligence. If a structure fails to deliver them, its integration is flawed. A system-based definition of an intelligent building combines advanced hardware with rigorous integration. While 3A hardware provides the baseline, the intelligence itself is a product of structural integration. This framework treats architecture as a holistic, active organism. Designing for intelligence requires ensuring the seamless flow of data across all structural boundaries. True building intelligence is an architectural state of being, an environment where automation, physical structure, and management protocols dissolve into a single, optimally composed system.